So we had filled in this table on Friday right before the bell rang. 480 out of 600 was 80%. And so if these events were independent, then 80% of the 200 people that could yes to evil eyebrow, and 80% of the people that said, 80% of the 400 that said no to evil eyebrow. If these events were independent, it would be 80% of all of these people and 80% of all of these people, because it should be 80% across the board. Remember, if events are independent, then it doesn't matter if another event does or doesn't happen. The percentage doesn't change. The probability doesn't change. So this bottom part, no to taco tongue, that was 20%. That's the 120 out of 600. So this 40 here is 20% of 200, with both of these pointing to this total. And that 80 is 20% of 400. And that's where our 400 is coming from. We could have done it the other way. I could have said that 200 is 1/3 of 600. And then I could multiply this by 1/3. And that by 1/3. 400 is 2/3 of 600. So I could multiply this right here by 2/3 and 1/3 to get here and here. I could have done the other direction. It doesn't matter what direction I'm going with this, because we're filling it out as if these events are independent, as if there's no relationship between these things. So I want to find these probabilities using our independent table. What is the probability of yes taco tongue? What is the probability that any random person that was involved in this said yes to taco tongue? It'd be 480 over 600, which is 80%. What about yes to taco tongue, given that they said yes to evil eyebrow? Here's my condition. 160 over 200, which would be what as a percentage? $160 out of 200 would be what? 80%. Yes to taco tongue, given that they said no to evil eyebrow. So now my condition, 320 out of 400, which would be what as a percentage? 80%. The overall probability that somebody could taco tongue from this group of individuals was 80%. If they could evil eyebrow, it was still 80% of those people that could taco tongue. If they couldn't evil eyebrow, it was still 80% of those individuals that could yes to taco tongue. Did knowing whether or not somebody could evil eyebrow help you, or could it help you make a better prediction about whether or not they could taco tongue? No. Because no matter what, it was going to be an 80%. I can't make a better guess about whether or not they can. It's 80%, so I'm probably going to guess that they can. But knowing the evil eyebrow status doesn't change my guess. It doesn't let me get a more precise guess here. What do you notice about the answers to question number 6 that we did on Friday, and the question to the answer to number 8 that we just finished up? Let's go back and look at number 8. What were all the answers in number 8? 80%. Was that true on number 6? No. What were our answers on number 6? 80%, 90%, and 75%. So what's different? What do you notice about number 6 to number 8? In number 6, something. In number 8, something. Yes. Yes. In number 6, all the probabilities are different. In number 8, all the probabilities were the same. All right. We're going to generalize this. We're going to complete the following statement using a formula. Let event A be yes to taco tongue, and event B be yes to evil eyebrow. If events A and B are independent, then the probability that event A happens is exactly the same as the probability that event A happens given that event B already occurred, which is exactly the same as event A happening, the probability of event A happening if event B didn't occur. The probability of event A does not change when event B does or does not occur. If my events are independent, then the probability of one event doesn't change no matter whether the second event does or doesn't happen. All right. Let's go ahead and flip over to page 13. When I'm talking about conditional probability, this is how our conditional probability notation looks. This is the probability of event A given event B, or I know event B happened. Whatever comes after that line, that thing already occurred, or I know that piece of information. The way we find that probability, I find the intersection of events A and B, and I can divide that by the probability for event B. Only my given event would be in my denominator. Independent events, when knowing one event has or has not occurred, does not affect the probability of the other event. It does not change it. This is what you guys just wrote down on the previous page. If the probability of event A is equal to the probability of event A given that B is equal to the probability of event A given that B complement, then A and B are independent. So if the probability of event A is equal to the intersection divided by the probability of event B, or another way of looking at that, if I can multiply the probabilities for events A and B together, and that comes out to be the same as the probability of the intersection, then these events are independent. Let's go and look at the check your understanding together. Number 1 says, find the probability of C given S. What does C stand for? Have 4 or more children. And what does S stand for? 1976. So how would I interpret this probability notation in context? Or do you want to find it first? Yes, Sarah. Absolutely. So let's find that probability, and then we're going to write that out as a full sentence so that we can actually put the probability in there. So the probability of C given S is equal to, does anybody remember how we are finding these probabilities? What do I need to put in my numerator? Yep, A and B, or in this case, C and S. What's going to go in my denominator? S. So where's the intersection of 4 or more children and 1976? 40. So that's my numerator. And what would the value for S be? I need all of S. 100. So 40 out of 100. What would that be as a decimal? 0.4. The probability, again, we're interpreting now, of a mother having 4 or more children given that she was surveyed in 1976 is 40%. The probability of a mother having 4 or more children, given that this interview took place in 1976, is 40%. Let's go look at number 2. Given that the chosen mother was not surveyed in 1976, what's the probability that she has 4 or more children? Write your answer as a probability statement using the correct symbols for the events. All right, so this is going to be probability of what? What would come right after this? C, 4 or more children. Given that, S complement. So I need the intersection of C and S complement in my numerator. And I need S complement in my denominator. All of S complement. So let's go back and look at the table. I want 4 or more children, not 1976. 26, we've got this, plus this one. So 13 plus 13 in my numerator. Over, what is S complement? 200, this one right here, plus this one right here. That's everything that is not 1976. So 26 out of 200. What would that be in its decimal form? 0.13 or 13%. So what happened as time passed? Were people as likely to have 4 or more children? No. 1976, there was a 40% chance any mother that was involved in this survey had 4 or more children. When this survey was repeated in 1994 and 2014, that number had gone way, way down. Are the events surveyed in 1976 and 4 or more children independent? Are they independent? No. How do we know just by looking at the work that we did up above? Yes. So knowing when somebody was interviewed would let you make a better guess about whether or not they had 4 or more kids. If you know that they were surveyed in 1976, there's a greater chance that they had 4 or more kids than if they were surveyed at a later time. So no, these events are not independent. Mothers surveyed in 1976 are more likely to have 4 or more children than mothers not surveyed in 1976. Or if I was going to use my probability notation to explain this, I would say that the probability of 4 or more children, so the probability of C given that S, is not equal to the probability of C given S complement. If those probabilities were the same, then they would be independent events. The probabilities are not the same, so they are not independent events. All right, let's flip over to page 15. I really wanted to have time to play this game, but I don't think we're going to have time today. So I'd still like to go through this exercise, though. We can still answer the questions without taking the time to play the game. So here are the rules of the game so that we kind of know the setup, and then we're going to fill in what's called a tree diagram. That's a way for me to help think through what these different probabilities are. The rules of the game. There's only 5 cards involved in this game. 2 aces and 3 kings. Player's going to choose their first card. They're going to record the results. Then they choose their second card. So the first time the dealer is holding 5 cards, the player takes 1 card, hangs onto it, and then they select their second card. If they get a pair, so 2 kings or 2 aces, they win. If they don't get a pair, so a king and an ace, then they lose. So far, so good? All right, let's see if we can fill in these probabilities. What is the probability that when they draw their first card, it's an ace? 2 out of 5. What's the probability that the first card they draw is a king? 3 out of 5. At the point in time that that first card has been drawn, whether it's a king or a queen, how many cards is the dealer holding now? 4 cards. If the first card they drew was an ace, the dealer still has 4 cards left, right? How many of those 4 cards, if the player is holding 1 ace, how many of those 4 cards could still be aces? 1. So the probability that the second card they pick is an ace would be what? 1/4. Probability that they draw a king? 3 out of 4, right? 3 out of 4. What about if the first card they drew was a king? What's the chance the second card they pick out is an ace? 2 out of 4. Because both of the aces would still be in the dealer's hand. What's the probability that they draw a king for their second card? Also 2 out of 4. The way we use our probability trees. Probability trees are showing me conditional probabilities. This 1/4 that we just filled in up at the top, that is the probability of drawing an ace, given that I've already drawn an ace. Or let me spell this out a little bit better. The probability that the second card is an ace, given that the first card was already an ace. So all of these probabilities in this second column here, these are all the probabilities based on our first condition. What did you draw first? With a tree diagram, I can find the probabilities of anything I want to by multiplying along the branches. So if I want to know the probability that my first card is an ace and my second card is an ace, I'm going to multiply the probability of getting an ace for the first one, so 2/5. I'm going to multiply that to the probability of getting an ace for the second card. What was the probability of getting an ace for the second card? 1/4. So what's the probability that I draw 2 aces? 2 out of 20. Which is the same thing as 0.1. What's the probability that the first card is an ace and then the second card is a king? What would I multiply together? 2/5 times 3/4. So what would this probability be? 6 out of 20. Which would be the same as what decimal? 6 out of 20 is the same as what out of 10? 30%, 3 out of 10. So 0.3. What's the probability that the first card is a king and the second card is an ace? What do I multiply together? 3/5 times 2/4. Which is what? 30%, 6 out of 20. What about the first card being a king and the second card being a king? 30%, 6 out of 20 again, because I would have 3 out of 5 multiplied to 2 out of 4. And so I get 6 out of 20 again, or 30%. What do you notice about this last column here, those probabilities at the end? They all add up to 1, yes. Why does that matter? Yes. That means that I've got a good probability model here. I'm showing all the possible outcomes for this game, and I know the probabilities of each possible outcome there. Let's see if we can find the theoretical probability of winning this game. Let me take all of this writing to the next page with us. Or on yours, it's just further down the same page. But for mine, I have to go to the next screen. There we go. How would I find the theoretical probability of winning? What does winning entail here? 2 aces or 2 kings. Is there any overlap there? Could somebody get 2 aces and get 2 kings in the same game? No. So there's no intersection. I need to use my general addition rule, but there's nothing in the intersection. So what's the probability that we get 2 aces? 0.1. So 2 out of 20, or 0.1. Plus, what's the probability we get 2 kings? 0.3, or 6 out of 20. So the probability that somebody wins this game would be 8 out of 20, or 0.4. We've got a 40% chance of winning the game. All right, let's see if we can answer question number 5 down at the bottom here. What is the probability that the first card was a king if we know the person won the game? Let's write our probability notation for this first. Given that the person won the game, where does that go in my conditional probability notation? Second. So the probability that the first card was a king, given that they were a winner. So I need the probability that the first card was a king and they won, divided by the probability that they were a winner. Sorry, I know this is squeezed in way down at the bottom of my screen. What did we say the probability that somebody was a winner was? 40%, 0.4 goes in my denominator. What's the probability that the first card was a king and they were a winner? 30%. That would be first is a king and second is a king. So right here is the probability that the first is a king and they're a winner. So 0.3. 0.3 divided by 0.4 is going to give me what? 0.75. So if this person won the game, there's a 75% chance the first card they drew was a king. If they won the game, there's only a 25% chance that that first card was an ace, because there's not as many aces in that deck, right? At least this special deck that we're playing with. All right, let's flip this guy over. General multiplication rule. The probability of the intersection A and B is equal to the probability of event A times the probability of event B given that A already happened. That's what we did when we multiplied along our tree diagram. The probability that somebody got an ace times the probability that they got a king, and given that they got an ace the first time, gave us the probability that they got an ace and then a king. If A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. So our tree diagrams can get really, really big. They usually don't go out past 3 places, like 3 branchings, because then it gets really complicated to look at. But these get used a lot when we're talking about statistics and probabilities. We're going to have A and A complement along our first branch. B given that A, B complement given that A. B given A complement, B complement A complement. This is going to tell us our intersections. When might this be useful to use? When might you want to do it this way? What have we been using before to find the probability of our intersections? We've got our two-way table, or we could also use what to find our intersections? Venn diagram. If I don't have access to all the information that I would need to completely fill in my two-way table or to completely fill in my Venn diagram, I might want to do it this way. I might have enough information to do this. Take about 5 minutes. I want you guys to try this. Start off by trying to construct a tree diagram. Once you construct a tree diagram for the situation that they're describing, the scenario, then I want you to try to answer questions B and C, but I am most interested, sorry, B, C, and D. I am most interested in your tree diagram. Those are different events. A, B, they're different events. P is the probability of them being alike. Of them intersecting, not necessarily being alike, but them happening at the same time. So I might have an event that I take my robe. I might have an event that it rains outside. So what's the probability? So if I'm looking at A, I'm going to bring my throw to one time. It would be the probability that it brought me. It would be the probability that it didn't bring me. So usually this is my not going to be 50 because I'm not ever going to throw my throw. So I have 0.5 of 3 times 0.1. Or you can write the probabilities here. You want to write your events here or your probabilities here. When I do this, I'm actually writing it here. What's the chance of it right here? So that we get most of the sense. Probability that I write my umbrella, 1. Probability that I don't write my umbrella, 5. This over here, we'll be talking about the second event. So what about the rains? So this one up here would be the probability that it rains if I brought my umbrella. I will write that probability down right here. What's the probability that it didn't rain if I brought my umbrella? What's the probability that it rains if I didn't? Sorry, this is what the probability that it didn't rain given my umbrella. What's the probability that it rains if I didn't bring my umbrella? What's the probability that it doesn't rain if I didn't bring my umbrella? And then right here. So you're going to multiply this probability together with this probability. That will give you the probability that those two things happen at the same time. And what does that mean when like it's independent? When it's independent, the probability of this does not change whether the second event happens or not. So the probability that it rains outside today, I don't know 50-50 on whether or not I'm bringing my umbrella. Knowing that I'm not bringing my umbrella or not, I can have to do it better guess over that. So the reason why this is not dependent on the side, your chances of drawing a So when I started drawing my tree diagram out, we started off, we've got our states, and the state either ended up going for the Republican or the Democratic candidate. The chance that they went for the Republican candidate, we had 30 out of 50, so 0.6. The chance that they went for the Democratic candidate was 20 out of 50, or 0.4. What was the other event that we're talking about here? Because that's going to be what I use for my second set of branches. Whether they were part of the continental U.S. or not. How many states do we have that are not? 2. So I have continental, not continental, continental, not continental. They told me here that 29 of the ones that went Republican were continental, which means 1 out of the 30 was not. It was either Hawaii or Alaska, not sure. Down here they told me that 19 of the ones that went Democrat were in the continental United States. So 1 out of 20 went the other way. So either Hawaii or Alaska went Republican, and the other state went the opposite direction. I want to find the probabilities now that a state went Republican and they were part of the continental United States. So I'm going to multiply along that branch. The probability they were Republican and continental, so I do 30 out of 50 times 29 out of 30. And I end up getting 29 out of 50 if I leave it written as a fraction. The probability that they went Republican given that they were not continental, 30 out of 50 times 1 out of 30. I end up getting the reduced fraction of 1 out of 50. I could write this down as 30 out of 1,500, and I'd have to multiply that together. I can't do that one in my head as easily. Out of 1,500. I used my rules of multiplication. I cross-canceled to simplify it. And then the probability that they went Democrat given they were continental, Democrat given that they were not continental. I got 19 out of 50 and 1 out of 50. You are welcome to write those down as decimals instead. I usually do when I make a tree diagram unless I'm working with really easy fractions. But these, I call these the leaves at the end. We've got our branches that we multiply along, and then we have our leaves out on the end. All those leaves should add up to 1. This should tell you the entire probability model. Using this tree now, what's the probability that a randomly selected state is in the continental United States and they went Republican? 29 out of 50. Or 0.58 if you write it as a decimal. If we selected 4 states at random with replacement, what's the probability that at least one of the states is in the continental US and went Republican? So if I want the probability of at least 1, that's going to be, honestly, a complicated number to find usually. But 1 minus none is a much easier number for me to find. So what is the probability that a state was in the continental United States and went Republican? What did we say that probability was again? 29 out of 50. So what would be the complement of that? What would be the complement of 29 out of 50? Not 1 out of 50. The complement would be 1 minus that. What would that look like? 0.42. So the probability that it is not Continental and Republican, 1 minus 0.58 or 0.42. I want to know if I select 4 states. So I've got all 50 states written on little slips of paper, and they're all in a hat, and I mix them all up. I pick out a slip of paper, and I look at it. The probability that it is part of the continental United States and it went Republican is 0.42. Then I put that slip of paper back in the hat, and I mix it around, and I pick out another state. I'm back at a 0.42, right? I do that 4 times. So for 4 states, I'm going to multiply that probability by itself 4 times, or 0.42 to the 4th. So to find the probability that at least one of these states was part of the continental US and went Republican would be 1 minus 0.42 to the 4th, or 0.9689. Given that a randomly selected state is not in the continental US, what's the probability that it went Republican? 0.5. Here's the way I would work that all out if I didn't have my tree diagram, if I didn't know that it was just those 2. The probability of Republican and not continental was 1 out of 50. The probability that it was not continental was 1 out of 50 plus 1 out of 50, or 1 out of 50 divided by 2 out of 50, 1/2, 0.5. I used my rule for conditional probability. 5.3 homework is due tomorrow. Tomorrow we're going to start reviewing for your test. We are definitely going to do some extra practice with probabilities that you guys will have a chance to do in class. And then we're either going to do some multiple choice or an FRQ. Whichever one we don't do tomorrow, we'll do on Wednesday. So we're going to get practice with multiple choice, practice with free response questions. Then I'll take questions from the test review from you guys on Thursday. Before you leave the room, please grab a copy of the test review. Have a great rest of your day, and I'll see you guys tomorrow.